Have a good day, sir. We are Group 4A. I'm James Jano. I discuss about hardware solution for the critical section problem. The critical section problem can be solved simply in a processor environment if we could forbid interrupts to occur while a shared variable is being modified. In this manner, we could be sure that the current sequence of instructions will be run, so no unexpected modifications could be made to the shared variable. So, unfortunately, this solution is not feasible in a multiprocessing environment, as disabling interrupts can be time-consuming as the message is passed to all processors. This message passing delays entry into each critical section and system efficiency decreases. Then, normally access to a memory location exclude other accesses to that same location. Then the designer have proposed machine instruction that perform two operations automatically indivisibly on the same memory location. This two is a reading and writing. Then the execution of such an instruction is also mutually exclusive, even on multiprocessor. They can be used to provide mutual exclusion, but other mechanisms are needed to satisfy the other two requirements of a good solution to the critical section problem. These instructions are the test and set, also known as test and set lock or TSL and swap. The semantics of the test and set instruction are as follow. This is the sample code of this. Boolean test and set means Boolean and target. Boolean RB equal target. Target equal true. Means ang true ag iyang return RV. Nag-return siya sa Boolean. Then, if the machine support test and set instruction, then we can implement mutual exclusion by declaring a Boolean variable lock. Initialize to false, the structure of process PI becomes do. We use a statement sa do while test and set lock critical section lock equal false means reminder section. Then the while is a critical section after the lock of the statement is reminder section. The above TSL based solution is no good because even though mutual exclusion and progress are satisfied, bounded waiting is not. The semantic of the swap instruction, another atomic instruction, are expected as follows. There's another code of a Boolean swap, Boolean and A, Boolean A and B. Boolean temp equal A and B temp. If the machine supports the swap instruction, mutual exclusion can be implemented as follows. A global Boolean variable lock is declared and is initialized to false. In addition, each process also has a local Boolean variable, K. The structure of process PI is, if the machine support the swap instruction, mutual exclusion can be implemented as follows. A global Boolean variable lock is declared and initialized to false. In addition, each process also has a local Boolean variable, K. The structure of process PI is this. We use again a dual statement and K equal true while K equal true, swap lock K. There's the code about the critical section, then lock equal false. This is a reminder section.
Hello, I am Mark Lester Hamela, the next reporter to discuss about the topic of lecture number 22, which is the hardware solutions. In algorithm 3, in this algorithm, we combine the ideas of the first two algorithms, which is the sample code we have seen in the screen. The common data structures used by cooperating process are. So the structures of process P is the do while loop and the while loop statement. The test and set is executed in this process. So the first process to execute the test and set instruction will find key equals false or equal false. All others must wait. The variable waiting I can only become false if another process leaves its critical section. Only one waiting I is set to false, maintaining the mutual exclusion requirement. To prove the progress, these data structures are initializing to false to prove that the mutual exclusion requirement is met. We note that process P can enter its critical section only if either waiting I equal false or key equals false. The value of key can become false only if requirement is met. We note that the argument presented for mutual exclusion also apply here. Since a process exiting the critical section either sets lock to false or sets waiting the variable g to false, both allow a process that is waiting to enter its critical section to proceed. Oh yeah. To prove that the bounding waiting requirement is met, we note that when a process leaves its critical section, it scans the array waiting in the cyclic ordering, or the I plus 1, I plus 2, and so on. It designates the first process it sees that is in its intersection with waiting the variable g equals true as the next one to enter its critical section. Any process waiting to do will enter its critical section within n-1 turn.
I'm Remark La Peña. Now I will continue to discuss our topic, which is semaphores. What is semaphores? Semaphores is a hardware solution to synchronization problems are not easy to generalize to more complex problems. To overcome this difficulty, we can use synchronization tool called a semaphore. A semaphore S is an integer variable that, apart from initialization, is accessible only through two standard atomic operations, which are wait and signal. These operations were originally termed P for wait and V for signal. The classical definitions of wait and signals are wait semaphore while semaphore is less than to equal 0, no operation. Semaphore minus minus. And the second one is signal semaphore S plus plus. And we can use semaphores to deal with the n process critical section problem. The n processes share a semaphore mutex standing for mutual exclusion. Initialized to 1, each process P is organized as follows. Though wait mutex or critical section, signal mutex or remainder section, while 1. In a uniprocessor environment, to ensure atomic execution while executing wait and signal, interrupts can be disabled. In case of a multi-processor environment, to ensure atomic execution, one can lock the data bus or use a soft solutions such as the Beccari algorithm. Semaphores. The main disadvantage of semaphore is discussed in the previous section is that it requires basic waiting. While a process is in its critical section, any other process that tries to enter its critical section must loop continuously in the entry code. This continual looping is clearly a problem in a real multi-programming system, where a single CPU is shared among many processors. Basic waiting wastes CPU cycles that some other process may be able to use predictably. This type of semaphore is called spin lock. A spin lock because the process spins while waiting for the lock. Spin locks are useful in multiprocessor system. The advantage of spin lock is no context switch is required. When a process must wait on lock and context switch may take considerable time. These spin locks are useful when they are expected to be held for short times. The definition of semaphore should be modified to limit PC waiting.
I'm Javier Canoy. I'm going to report lecture number 23 and continues to report this. This spin lock is expected to be held for short time. Spin lock are useful to overcome the needs of busy waiting. We can modify the definition of the semaphore and the wait of the signal operation. When the process execute, the wait operation find that semaphore value is not positive. It must wait. However, rather than busy waiting, the process can block itself The block operation places a process into waiting queue associated with the semaphore, and the state of the process is switched to the waiting state. Then control is transferred to the CPU scheduler, which select another process to execute. A process that block waiting on the semaphore should should be started when some process execute a signal operation. The process is restarted by a wake up operation which change the process from the waiting state to the ready state. The process is then placed in the ready queue. The CPU may or may not be switched from the running process to the newly ready process depending on the CPU scheduling algorithm. Such an implementing of a semaphore is as follows. This is the code that going to execute. Each semaphore has the integer value and a list of process. When the process must wait of the semaphore, it is added to the list of processes. A signal operation removes of the process from the list of the waiting process and awaken that process. The wait operation can be defined as this code wait semaphore s if value less than 0, add process to SL block. The signal semaphore operation can be defined as this code void signal wait semaphore s is that value increment if s value is less than equal to 0, remove the process from the ls and wake up. And the block operation suspend the process that invokes it. The wake up p operation resume the execute of the block process p. These two operations are provided by the waiting operating system as a basic systems calls. The negative value of s value indicates the number of the process waiting from the semaphore. A pointer in the PCB need to maintain a queue of the process waiting for the semaphore. As mentioned before, the basic waiting version is better than critical sections as a small of queue waiting. Before is better for long critical section when waiting is the longer period of time. You can use semaphore to synchronize cooperating processes. Consider for example that you can execute statement B in PG only after statement A has been executed and pi. You can solve this problem by using smartphone as initialized to 0 and constructing the code by pi and PG as follows. PI wait signal B PIA. PG will not able to execute statement B until PI has executed its statement at A signal S. Here is another synchronization problem that can be solved easily using smartphone. We can to ensure that statement S1 and P1 executes only after statement S2 and P2 has executed, and statement S2 and P2 should executed only after statement S3 and P3 has executed. One possible semaphore-based solution used two semaphore A and B. Here is the solution. Semaphore A 0 B 0 P1 P2 P3 wait E wait B S3 S1 S2 signal B signal A. Problem with semaphore. Here are some key points about to use semaphore. Semaphores provide powerful tool for enforcing mutual exclusion and coordinating processes. The wait and signals operations are scattered among several processes. Hence, it is difficult to understand their effect. Usage of semaphore must be correct in all processes. One bad or malicious process can fail the entire system of operating processes. Deadlocks are starvation. A set of processes are said to be a deadlock state if every process is waiting for an event that can be caused only by another process in a state. Here are a couple examples of deadlocks in our daily life. Traffic deadlocks, one-way bridge crossing. Starvation is in infinite blocking caused due to unavailability to resources. Here an example of deadlock. POP1 wait is wait signal. That was the code. P0 and P1 need to get to semaphore A's and Q before executing their critical section. The following code structure can cause deadlocks involving P0 and P1. Can example P0 grab example S and P1. Obtain semaphore Q. Then PO waits for Q and P1 waits for P0 waits for P1 to execute signals. Q and P1 waits for PO to execute signals. Neither process will execute the responsive instruction. A typical deadlock situation. The following diagram shows that the situation pictorially signals. So that was the illustrations of the deadlock situations. So here is an example for starvations of the code structure are self-explanatory. P1, P2. So that's what. Violation of mutual exclusion. In the following example, the principal mute exclusion is violated. Again, the code structure are self-explanatory. P0, P1 signals. That was structure, self-explanatory. This problem are due to programming error because of the tandem used to wait the signal operations. The signals to problem and higher level language structures such as signal region statement and monitor. So this was the last slide that I report. This is the group member, Jindy Sigera, James, Remark, Javier, and Lester. So that's all. Thank you.